What if your coding assistant could pause, decide it needs more time, and then ship a real fix hours later? We all know the scene. An assistant auto-completes a few lines, tests fail, and you spend an hour rescuing the build. That friction adds up into wasted focus and botched releases. Now imagine a different flow where the AI doesn't quit at the first blocker. It plans, runs tests, and returns with a working pull request. That change sounds small, but it reshapes who touches the keyboard, and we'll unpack how in the next scene. Meet GPT-5-Codex, a specialized model built to act like an autonomous engineer. It reads repositories, writes code, runs tests, and writes review comments. Crucially, it decides its own thinking time during a task. Instead of a fixed burst of steps, it reassesses complexity and requests more compute when needed. That shift turns short bursts of autocomplete into sustained problem-solving across files and CI pipelines. But what does thinking longer actually look like in practice? Think of it as a senior engineer who says, "Hang on, I need more time." The model might start a refactor, hit unexpected edges, and then request 5 minutes, an hour, or even several hours to finish. OpenAI reports internal runs over 7 hours on big refactors, where the agent fixed tests and shipped solutions. That capability is the headline, dynamic thinking time. But of course, long thinking isn't free, and there's a trade-off coming up. Why does variable thinking time matter? First, fewer mid-task interruptions. The agent won't stop at the first surprise. Second, better end-to-end outcomes. It can integrate, run tests, and iterate in one flow. Third, it handles high-leverage problems where static time models give up. For teams, that means less babysitting and more shipped work. But before you hand over your repo, you should weigh costs and guardrails, which we'll look at next. Longer runs consume more compute and therefore cost more. Reserve extended thinking for high-impact work. Migrations, large refactors, and critical bug hunts. Treat dynamic time like a budget line item, per task ceilings and tags for cost allocation. Many organizations find the ROI quickly. An agent that saves days of human time can justify hours of compute. Still, cost control is only one part of safe deployment. The next section covers how the model improves review quality itself. GPT-5-Codex isn't just an automated commenter. It produces fewer incorrect comments and more high-impact suggestions, according to evaluations. Engineers noticed it flags subtle backward compatibility risks that human reviewers missed under time pressure. That moves the tool from a linting assistant to a second pair of eyes that reasons about system-level risks. It can also open a PR with a clear rationale, not just edits, but how does it validate those suggestions? Let's follow the test execution story. One strength is repository-wide awareness. The model reasons across modules, dependencies, and tests. It runs unit and integration suites to validate suggestions, reducing brittle advice. It can trace a failing test back through service boundaries and propose fixes that actually resolve CI failures. That reduces the classic works locally, breaks in CI problem. Next, we'll look at benchmark results that reflect these practical gains and what they mean for real repos. On benchmarks, GPT-5-Codex outperforms the base GPT-5 on agentic coding tests like SweBench and on large refactor tasks from real repositories. Those benchmarks simulate editing, running tests, and verifying fixes end-to-end. Benchmarks don't capture everything, but they indicate fewer surprises in CI and better decomposition of multi-step problems. That capability becomes essential when switching context across tools, which is the next friction this model targets. Context loss is a recurring developer complaint. You start in the IDE, jump to GitHub, and your assistant forgets the failing tests. GPT-5-Codex integrates across terminal, IDE, GitHub, web, and mobile to keep context synchronized. Kick off a long refactor locally, walk away, and later review diffs and test outputs on your phone. That continuity multiplies productivity for distributed teams. But how does this stack up against other tools in the market? The market is competitive. GitHub Copilot dominates inline completion and daily workflows. Cursor emphasizes an agentic IDE experience. Windsurf draws strategic interest for autonomous coding. If Copilot is the always-on code typer and Cursor is a nimble agent inside the IDE, GPT-5-Codex positions itself as the cross-environment engineer for long-running, repository-wide work. That positioning matters when you pick tools for day-to-day versus heavy lift tasks. So who actually benefits most from Codex? Best fits include teams with solid test coverage and mature repositories, back-end heavy systems, frequent refactors, and organizations that run CI reliably will see the biggest gains. Startups with growing complexity can use it for infrastructure and debt paydown. Front-end teams with extensive component tests can also benefit. But there are scenarios where it's less helpful. Next, I'll flag the cases where you should think twice before handing over autonomy. Avoid relying on long-run autonomy in greenfield projects with few tests. Highly ambiguous specs are risky too. AI needs clear outcomes. Time-sensitive hotfixes often require a human touch for speed. And when cross-team coordination or architectural trade-offs matter, human judgment should lead. The model excels with clear guardrails. That leads to a practical setup checklist you can implement today, starting with repo hygiene. Step 1. Prepare your repo. Ensure tests run locally and in CI. Fix flaky tests. Add type hints where feasible and document service boundaries. Expose clear test runners for unit versus integration suites. These steps give the model signals to validate against and reduce false positives. A prepared repo turns autonomous runs into predictable outcomes. Next, we'll configure access and guardrails to keep those runs safe and auditable. Step 2. Configure access and guardrails. Grant read-write on a feature branch rather than main. Enforce status checks and required reviews before merge. Enable secret scanning and dependency checks. Log agent activity and require audit trails for long runs. Those controls let the model iterate without bypassing governance. After that foundation, set task scopes and budgets so the agent knows the runway for each task. Step 3. Set clear task scopes. Use crisp objectives like refactor X to Y or migrate endpoint A to B. Attach failing tests, constraints, and performance targets. Define a time and compute budget and allow the model to extend within your limits. For example, allow up to 2 hours extra thinking for migration tasks, but stop if tests fail repeatedly. Clear scopes prevent scope creep and keep runs accountable. Next, add feedback loops. Step 4. Build feedback loops. Start with dry runs: proposal, plan, diff, test, review. Ask for a risk report and a compatibility checklist with each PR. Track outcomes like pass rates and revert frequency to tune prompts and budgets. These loops turn opaque runs into measurable experiments. After you have feedback, run across environments, kick off locally, run remotely, and review in GitHub. I'll explain that flow next. Step 5. Work across environments. Start tasks in your IDE for local context. Let the agent run longer jobs via CLI or Cloud Agent. Review diffs, test outputs, and risk reports in GitHub. Triage comments on web or mobile while away from your desk. This continuity reduces context switching and keeps busy engineers productive. But before you trust long runs, consider costs, privacy, and compliance. The next section covers those governance essentials. Dynamic thinking requires governance. Set budget controls and per-task cost ceilings. Prioritize long runs for high-impact work. Confirm how code is processed and stored, with encryption and audit logging for enterprise needs. Align with SOC 2 or ISO standards if required, and avoid production secrets in prompts. Route agent changes through SAST, DAST, and dependency checks. Guardrails let the model do deep work without opening security holes. Now, let's explore concrete scenarios where this actually pays off. Large-scale refactor in a monorepo is a classic high-leverage task. The agent maps call sites, updates SDK usage, adds adapters, and runs integration tests. It can propose a staged migration plan and generate a migration PR. That's weeks of manual work condensed into a guided, validated run. Another common win is framework migration, updating deprecated APIs and patching tests. These are the sorts of problems where long thinking shifts outcomes dramatically. Other high-value scenarios include API versioning without breakage, performance regression hunts, and test coverage uplift. For performance issues, the model can add instrumentation, compare traces, and suggest schema or index changes. For coverage work, it enumerates critical paths and adds targeted tests. These tasks consume engineering weeks and are where autonomy delivers the largest ROI. But it's not flawless. Let's flag the limitations you should expect. Limitations matter. The model struggles with ambiguous requirements, missing or flaky tests, and cross-team coordination. It can propose architectures, but product trade-offs still need human sign-off. Long runs are non-deterministic. Different seeds and environments can yield varying plans, so lock down configs for reproducibility. In short, give it clear runways and keep humans as final arbiters. Next, let's compare it directly to the tools you already know and use daily. GitHub Copilot stays excellent for inline assistance and quick completions. Cursor focuses on agentic IDE experiences and rapid iteration. Windsurf signals strategic interest in autonomous coding. GPT-5-Codex differentiates on long-running cross-environment work, deep review, and repository-wide reasoning. You don't need one tool for everything. Many teams will use Copilot for speed and Codex for heavy lifts and reviews. Want a concrete prompt pattern to get safer results? I'll give one next. Use a disciplined prompt pattern. Objective, constraints, validation plan, deliverables, budget. Example, refactor payment gateway to Y. Keep V1 compatibility for 2 releases. Do not change public method signatures in Module A. Run all unit and integration tests. Open a PR with diffs. Test results, risk report, and rollback plan. Extend thinking time up to 2 hours if needed. That structure reduces ambiguity and improves reviewability. Finally, why does this matter to businesses now? The market signal is loud. Autonomous coding is moving out of labs into budgets. Cursor's growth and acquisition interest across the space show demand. Copilot proves developers want assistance all day. GPT-5-Codex pushes the shift from assistive tools to autonomous engineers by adding dynamic thinking, better review, and context continuity. If your organization needs faster shipping without burning teams out, this is a practical lever. Ready to try it safely with guardrails in place? If this helped, like and subscribe for more practical AI tooling guides. Tell us in the comments what task you'd hand to an autonomous coder first.